Thank you everyone for joining us today. Our speaker today is Bruce Nagy from Climate Solution Group, Toronto, Ontario. And Bruce will introduce Linda Parkinson, who is a manager of Falls Creek Neighbourhood Energy Utility, Vancouver. I'll begin by land acknowledgements. We're grateful to be able to join you from the traditional lands of the Mississaugas of the Credit, the Anishinaabe, the Haudenosaunee, and the Wendat. I'll stop sharing my screen now and invite Bruce to take over. Thanks, Bruce.
Okay, thank you very much. Well, welcome everybody, and thank you for coming. Pretty excited about this one. Linda Parkinson, a real expert on something that is a Canadian success story and a technology that is really making a big impact. And it's one of those untold stories. It's one of those under the radar stories. You don't hear a lot about it. It's sort of, it feels like an industrial process. It's going to be great. So, but I'll let her tell you all about it. But our topic today is energy recovery in general. So Linda's project has a certain kind, and then I'm going to talk about a few other kinds. And some of the kinds involve communities, they involve arenas, they involve data centers. I guess Linda will talk about Vancouver carbon reduction policy in general, which I think will be of interest to many of you who are municipal planners. She'll talk about the project, and she'll talk about some of the milestones in the future of that project. And as I said, I'll talk about other kinds. I'll talk about the built environment. I'll talk about the kind that Linda's involved with, and data centers and refrigeration. Now, Linda, she's a professional engineer. I'm going to do her introduction now, and I'll just switch over to her when it comes time. She has 20 years of different experience, including water and waste water utilities and waste management and district energy. And she's been managing the City of Vancouver neighborhood energy system since January of 2020. And before that, for 5 years, she was with Metro Vancouver, where she did the source control program within the wastewater department. And she has held leadership roles in local government and consultancy in Canada and in Ireland. And in addition to her engineering qualifications, very educated person, has a master's of business admin, and she's currently the vice president of the BC Water and Waste Association. So really glad to have her with us. Thank you for coming, Linda, and thank you, Juliet, for accommodating today's webinar. Who am I? If you've been on this one before, you know this. For the last couple of years, been doing these webinars with the Clean Air Partnership. I'm a columnist, was a speaker pre-COVID, not doing much speaking except on webinars these days. A bit of a consultant to corporations for clean energy, author of, this is what I do mostly, is author of 200 plus articles, and it might be more than that now, it is more than that, on climate solutions. And I have a book too, Clean Energy Age, so please buy the book. As mentioned, I want to talk about the energy recovery in the built environment in a general sense. And first I'll talk a little bit about ERVs and HRVs just as a means to talk about the principles, some of the principles involved. And then I'll talk about the other three areas that I've already covered. So I guess one of the best ways to understand energy recovery is, well, I guess what it is it's in liquid systems or air systems in buildings where you are using energy that in conventional times in the 20th century, we would just let fritter away. They would that energy would go down the drain or out the vent. So here are some simple technologies, modern ones, I guess, or new to us. A heat recovery ventilator or an energy recovery ventilator. I'm sure you've heard me talk about these many times relating to the modern tight buildings, the passive house buildings or the other kinds of tight buildings. So they supply a fresh air into that modern well-sealed home, and at the same time they are retaining the heat or cooling energy from the stale air that's being replaced. So, hot air is two things. It's hotness, it's air. And so this device separates the hotness from the air, and it keeps the hotness, expels the stale air, brings in the fresh air, and puts the hotness back into it. And if you want the device to do humidity management, then it's the second one. It's called the ERV, the Energy Recovery Ventlery. And another example of the same sort of thing, of retaining the energy instead of frittering it away, is down the drain. So here's a very simple device. It's been around for 20 years at least. It's a bit of a Canadian success story. I won't go there. But anyway, in a normal house, if you look at the left house, the side on the left of my screen, the cold air, the blue line comes in, the cold water, sorry, comes in, and it goes into your water heater where it gets heated up, and you take a shower. Then the hot water that you just showered in goes down the copper drain pipe right in the middle of that house, and it goes down into the sewer. Okay, so out goes the energy. Well, with this device, they just change the incoming a little bit, and they have the cold water comes in, and it's copper. Though the drain pipes are all copper because that's code. So this device is also copper, and copper is very good at convecting heat energy. So they just wrap it around the drain pipe. There's no moving parts. There's no mixing of water. It's two separate streams. But it just convects the, I'm not sure if I'm using the right term, it just moves the heat from the drain into the incoming cold, and it pre-warms it, saves tons of energy. And I was shocked to find out it saves about half your energy. And these things are now they're coded in their building code in many places. I don't know all the cities that have done it or all the states, but I know that it's increasingly being used. Again, I think it started in Europe probably, and then it came to the States. It might have been invented by a guy in New York. There's some dispute about that. But anyway, okay, so those are examples of very simple technology. And actually this one, the latter one with the water, is kind of what Linda's doing, but I'm gonna let her explain that. It's just on a much bigger scale with much different technology. She uses, for example, big heat pumps, big, heat exchangers, big holding tanks. So I'm not going to go into that too much. What I'm going to do is I'm going to talk about other projects similar, also sewer heat recovery, that are not Linda's in Vancouver. So one of my favorite ones is DC Water headquarters in Washington, DC. And it's one of my favorite ones because the system was provided by a Canadian company, Lynn Mueller's Shark Corporation. And they have this product. And after a lot of due diligence that DC Water headquarters did, because they wanted to show, they wanted, to show off and demonstrate, the state of the art, they looked at the European one. There was a really good one in Europe, and they looked at Lynn Mueller's, and I presume they looked at whatever's being used by Linda in Vancouver, which is more of an engineered solution over time, and they selected the Shark for. It may or may not be the best one for somebody else, but for what they were doing, whatever the parameters were, it was the best one. And as it turns out, it has served them very well. I'm going down there next month. They're giving me a tour, and I'm going to learn more. So I'll update you on that. But in the winter, I guess, Lynn Mueller says the water is about 20 degrees warmer than the outside temperature. In the summer, it's 20 degrees cooler. So the Shark system, therefore, saves, he says, 35% on air conditioning, 85% on heating. That's a lot. And 4 to 6 million gallons of water, which would have been used in the cooling towers. They do have cooling towers, but they're kept for backup in case, this system goes down, but they don't seem to go down. Anyway, you can ask Linda, maybe they do. And so the Shark system, I won't do too much of a commercial on them, but he has installed them all around the world, as you can see from the last sentence there. Here's another story of Canadians doing sewer heat recovery to help in the States. So in Denver, they've got a new National Western Center. I guess it's like a rodeo place that they're building or rebuilding on a site. and it's going to be 1 million square feet. And NWave, which is a Toronto company, they do the deep water cooling in Toronto. They're going to operate it, and so it's 1 million square feet. It's going to all be, the whole thing is going to be heated and cooled with the sewer energy, and and just as an aside, I guess Denver has a 141-year-old steam heat district system. It's been losing customers, I think, because prices are going up and the greenhouse gas concerns and so on. So that's sort of an aside. Here comes sewage heat. It's, I guess, new to you, sort of a modern thing, and it's got good energy economics. It's got low greenhouse gas. So and another sort of dimension on this is what this gentleman's comment was: with the advent of large-scale heat pumps, we can cost effectively use like 70-degree wastewater to heat our buildings and hot water systems, which is a technical improvement, because when in a conventional water heating situation for like domestic hot water that comes out of your tap, that's 160 degrees or something. So they're using gas, and the old timers naysayers will say, oh, you gotta have gas, you gotta have BTUs to get it up to 160. Well, with the advances in heat pumps, you don't. You can use 70 degrees as your source, and it has a very high coefficient of performance and so on. The King County one, it's also an American example. I come to Canadian examples soon, folks, don't worry. And in this case, there's a Canadian dimension. But they are now offering sewer heat recovery to commercial property owners and developers, and they are you know, to heat your buildings or cool your buildings. And the Canadian dimension is the sentence at the bottom. Sewer heat recovery technology is fairly common in Europe and parts of Canada, but standardized SHR use agreements are new in the US. So they are recognizing our greatness. Okay, I'm going to turn now to data center energy recovery. It's a different kind. Let me take a drink. So when cooling a data center, either with air systems or with liquid systems, which is becoming more common now because it's just more efficient. Liquids are more efficient at cooling system. You remove heat, and then you can reuse that heat for offices or multifamily residential or greenhouses and so on. Now, there was a movement in that direction, pushed by great authors like me writing articles about it 10 years ago, but it's kind of stalled. And why did it stall? Because the big four, somewhere in the middle there, the big four public cloud companies, they decided, and that I'm talking about Amazon Web Services, Google Cloud, Microsoft Azure, and Alibaba Group. They decided they wanted to, you know, create the cloud business, make lots of money, and move all the data centers all over the world onto their public cloud. And, you know, while they were doing it, they were also recognizing that all of us are Netflixing more, e-commercing more, social mediaing more, and our data is just going up, up, up. The amount that we use the internet is just increasing. It's not decreasing. So that was a big problem for them because it's an energy hog. And so they tackled, at the same time as they started moving everybody to the cloud, they also started tackling becoming very green. So there were two halves to the problem of energy with data centers. One half was computing itself, and the other half was cooling these big data centers. And it was just about 50-50, it used to be. But over the years, it has changed. The numbers have changed, and they've both gone down. The computing has gone up, and so greenhouse gas has stayed about flat, but computing has gone way up. And these big players have done a good job of A, finding efficient ways to do computing, and B, much better cooling systems. And while they were testing these systems, liquid systems, air, free cooling, they would put computer servers up north in the Netherlands and in Canada in cages outside to cool them, just free cool, or they would actually Microsoft dumped them right in the ocean inside of a metal thing, trying to find ways to cool that were efficient. And while they were doing that, they were distracted away from energy recovery, just like reusing that heat. Well, now they're starting to come back to it. But back a few years ago, here's a great example in Vancouver. TELUS built their new head office. And when they were building it, they were moving a bunch of sort of disparate offices all into one. And they knew that there were going to be employees moving into Vancouver. So they built the condo. That's the yellow thing in the bottom illustration there. They built that. It's also in the top right in the photos. So that people and new employees could buy condos in the city, and they had this blue. See the blue building in the illustration? That was an existing data center. So they built the other two buildings, and they were new. And so the existing data center had all this heat, and they recognized that the heat could be used in the daytime in the office, and in the evening and night in the condo. And that's exactly what they're doing. They've got sophisticated controls. They're moving that excess heat out of the data center and into the condo and the office tower. And it saves 80% over a comparable conventional sort of building project. So that's an amazing one. I love that example. Here's another one similar, smaller. QUÉBECOR has a data center in Winnipeg. And the gentleman's quote says it all. Well, it was 35 degrees Celsius outside, because it's Winnipeg, right? I would be paying a tremendous amount of money to cool the data center and to heat the rooms around it. So, why don't you get a technology, which they did, a heat recovery technology to, funnel that heat out of the data center into the offices. It seems like a no-brainer. And then they still had heat left over, so they started funneling some of it upstairs to the Winnipeg Sun newspaper offices, and also downstairs into a warehouse next door where they kept opening all the dock doors, and it had terrible insulation, and it worked. He said we were concerned we wouldn't have enough excess heat capacity, but we were actually running out of places to apply it. So, and that's a familiar story, which I'm going to tell when I get to arenas. I got to just check my time here. Facebook, this is a great one. In Denmark, operates two buildings, 50,000 square meters, I guess, in Odense, Denmark. I'm sure I'm saying that wrong. Facebook has partnered with a utility, and they're in the servers, and they transfer using copper coils and blah, 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 and they warm homes. 6,900 homes when it's at capacity. So pretty impressive. And in addition, in this case, Facebook's data center is already wind powered. So it's wind power, it's clean energy in the first place, and then the heat that it generates is shared with the community. North Vancouver, in this case, Lonsdale Energy Corp, provides district energy for heating, cooling communities, industrial process in North Vancouver, and it has entered into an agreement with a cryptocurrency company. Proponents say the arrangement will reduce greenhouse gas by 20,000 tons per megawatt by reusing heat from the cryptocurrency mining operation, which requires massive amounts of computing power 24/7, 365 days a year. Cryptocurrencies are controversial instruments that at best, I'm reading this for a reason, at best can be seen as non-sovereign trading platform, and at worst as an anonymous high-risk currency on the dark web used for ransom demands in cybercrime. And I'm not going to be cynical, I'm just going to the next screen. Stockholm, less cynical example. 900,000 people live in Stockholm. They have something called the Stockholm Data Parks, which warms 2,500 residential apartments in this one situation, again, using the data center. And then there's another group called Data Centers by Sweden. It's launching Stockholm-like projects, so it's scaling it. It's finding it scalable. They say that 10 megawatts of energy heats 20,000 modern residential apartments in Sweden. And I guess because the Facebook data center is 120 megawatts, that's 240,000 homes. So there seems to be a great potential here And the rest, I'm not going to go into the rest. It has some extra information for you all about that project. Here's a smaller one, but older. Way back in 2008, Paul Brenner, a researcher, he decided, let's put some computers in a greenhouse that's next door to the Notre Dame University in a conservatory. So they did that, and they've been ever since. And he put fancy controls so that he could do sensors, sense the temperature, and do more computing or less computing on that cluster of computer servers when needed. And he also monitored the particulate and the humidity to see if there would be, problems over the last, I guess, 12 or 13 years. There haven't been any real concern. I'm sure that it's different in some of the more sophisticated big operations than in this little situation. Similar thing in IBM, Switzerland uses a data center right beside a swimming pool, and they heat that. So for you municipal planners out there, greenhouses, swimming pools, these are, public kinds of things, good ideas, right? Small scale, big scale, it can be done. And arenas, I think, are one that you would be familiar with. I've talked about it before. In fact, I've done webinars on it. And last year I did this webinar, and that's where these 4 screens come from. And I was talking more about the natural refrigerants at that time. And I kind of glossed over the heat recovery itself, which is actually a big story. Like each of these arenas, first of all, these NHL arenas, and also some of the smaller ones, such as Upper Canada College, they're recapturing energy. And in the case of Upper Canada College, as I was joking at the last webinar, it was overkill. They were redoing, they have lots of money at Upper Canada College, so they put geothermal underneath the soccer pitch too. And as the big Canadian company Echo Chill, I think it's called, in Canada, or is it Climatech? I don't know. Dave was telling me that this is very efficient. Most arenas have small snack bars, like maybe not the NHL ones I was showing you, because they're warming up their customers on the bleachers. But in most little arenas that we have in small towns all across Canada, curling rink, arena, there's the snack bar is small, and the amount of heat they get from ice making equipment is big. And Climatech, I think, delivers the thing on a skid, and it's already got heat recovery technology in it, and it just heats the whole snack bar. You don't need a heating system. And so arenas are a great one. Here's a brand new one in Bentley, in Boston, that they put it in. And one of the things they did here in this arena and in another arena that's similar but not the same is, you know how the Zamboni goes out the garage door to put the snow outside, and all the cooling energy, or all in the summer cooling energy, all in the winter heating energy goes out the door with it. Well, now how can we do that to get rid of the snow, the ice from cleaning the ice, right? Well, we cannot open the door, and we can make a pit, which they do now, and they did it in this modern arena and in another Canadian one. And they just use the low grade heat that comes out of the ice making equipment, just to put some hydronic tubes in there just to melt the ice, right? So they just have a pit, an indoor pit, and they don't have to open the door. So that's an interesting sort of sideline. They did that here too. This one I'm not going to go into. It was a recommissioning. It was engineers arguing with engineers and fixing everything and saving tons of money. And it was it's the same thing. It's heat recovery on arenas. Then there's the grocery store one. Again, you're probably familiar with it. And again, it's a great success story, like the sewage one in the Vancouver area. In Quebec, they've been developing for a long time transcritical refrigeration systems. Now, they started in Europe, like most of these energies tech do, but they, always seems to be in America, oh, it won't work here unless we do this or that or this. So there's always got to be someone who's developing it for the North American market. Well, that somebody seemed to be a couple of companies in Quebec on the early days, and now there are bigger companies doing it, and now there are all the grocery stores all over America are going to transcritical systems, and that's where they use the refrigeration equipment to heat the store, and they don't need a heating system in the store at all because there's so much heat. And and again, I had these screens in a webinar last year, and again, I was talking more about the natural refrigerants, CO2, which again, bragging rights to Canada. They started to turn these things into CO2 as a refrigerant, which CO2, it's counterintuitive, but it's actually a natural refrigerant. So okay, I'm gonna go on. You have these screens. These are all examples of stores, 63 stores. Sobeys, that was one of the first ones that are recovering the energy from the refrigeration. Longo's has 13 stores. This one's new in Stouffville, Ontario. Loblaw, I'm more cynical about them. They kind of drag their feet and they kind of leverage some government money. And then, of course, you can do it in seafood plants, big refrigerated plants too. Same thing. There's a big Walmart one in Edmonton, and there's this one which is out in St. John's, and they're saving all kinds of money by just using what they've got on site. They're using the refrigeration. So I think I'm getting close to the end of my half hour. I want to turn it over to Linda. So Juliet, if you could please switch it to Linda Parkinson.
Thanks for bearing with me, and thanks for the introduction, Bruce. I have a presentation for you. This is an overview of what I'm going to cover today. I'm going to talk a bit, I think Bruce mentioned this, about general overarching policy within the City of Vancouver, and then tell you a little bit about how the neighbourhood energy utility started pre-2010, and then when we became operational in 2010. I have some pictures and some slides about our Falls Creek Energy Centre, which is where our heat pump, soon-to-be heat pumps are housed. And I guess to that topic, talk about the low carbon expansion or the sewage heat expansion project that we have ongoing at the moment. And then I'll end with a future look at what our main priorities are now and in the next few years. So in terms of policy context, Vancouver has a relatively long history addressing climate change. The Greenest City Action Plan was in place that saw a reduction in emissions over a 2007 baseline of about 9%, and that's in the face of a rapidly growing population. But we have a lot more to do, and Council have set some pretty aggressive targets. Where our current target is to reach 50% reduction by 2030. I'm sure lots of you are aware, maybe it's the same in your municipalities or cities, but within Vancouver, we know from inventories that 54% of emissions come from natural gas use in buildings. So heating and cooling buildings is a big area that we know we need to focus on to reduce emissions. And in 2019, the City Council unanimously declared a climate emergency. And then on foot of that, staff brought a climate emergency action plan to Council at the end of 2020, which was passed. And it centered around six big moves. The key one for the neighbourhood energy utility and where we contribute is here under Big Move 4, which is centred on zero emission space and space heating and water heating. And within that climate emergency action plan, our utility has committed to bringing a roadmap to Council to transition the utility from 70% renewable energy, which is our current target, to 100% renewable energy by 2030. I'll talk a little bit now about our utility and the origins, and just to orient everybody, if you've been to Vancouver, you know this is the North Shore, here's the downtown core, Stanley Park, and so this body of water here is what we call Falls Creek. It comes right into the Science World building, which maybe you might have visited. And so when I talk about Southeast Falls Creek, this area here in yellow is the area of the city that I'm referring to. And so this was the initial service area of the neighbourhood energy utility. We were called the Southeast Falls Creek Energy Utility. We've since expanded outside of that core area, and so now we usually go by the Falls Creek Energy Utility or just the neighbourhood energy utility. And so that area, that Falls Creek area, that Southeast Falls Creek area of the city was a brownfield site. Years ago, it was heavily used by industrial use. And the development plan, the ODP that was approved in 2006, approved 6 million new square feet of development in that area and over 16,000 residents. So high density, which is very suited to district energy. And so I guess that's one of the driving reasons why the decision was made to use a low carbon district energy system to provide heat and hot water to those homes in place of using natural gas boilers, which would have been the kind of business as usual at the time. And so that gave birth to what became our neighbourhood energy utility. We are a city-owned utility. We provide low carbon heat and hot water to now 43 customers. We target 70% of our energy coming from renewable sources. That's primarily our heat pump. And we also purchase a blend of renewable natural gas from Fortis BC. We've been operational since 2010, and yeah, we have around over 6 million square feet of buildings connected, which is getting close. I think we've actually just this year surpassed what the original business case was, but we have, through approved expansion plans through council, we are planning to grow to 22 million square feet over the next 20 years. And so this map will help you see some of those expansion plans. So to orient you again, this is Science World. The North Shore Mountains will be this way, the downtown core. And so here we are at the Falls Creek Energy Centre. We're tucked under the Canby Bridge. So this is our main energy producing facility. We have an existing, since 2010, a 3.2 megawatt sewage heat pump, a train heat pump, and we're currently in the process of installing a second heat pump. And that heat pump will have a bigger capacity, a 6.6 megawatt capacity heat pump. Just this year also, we commissioned a satellite boiler plant in the Mount Pleasant area. This here is Main Street in Vancouver, and this area is the Mount Pleasant area. We commissioned a 5 megawatt. It's mainly a peaking plant, and will also be used for added resiliency for the system on those very cold days. And so as well on this map, you can see our shaded area is what we call our service area or our mandatory connection area. And so a building within this shaded area has to connect to the NEU. We have a mandatory connection bylaw that requires connection, which is like really essential because it provides us with load certainty. You can see in red our current customers, most of which are like, this is the oldest part of the system. This is the original service area, which was the Olympic Village when Vancouver hosted the Olympics in 2012. And so this here is the area we call Southeast Falls Creek. And as you can see, we have expanded out into Great Northern Way. This is Emily Carr University, and up into Mount Pleasant. And I'll touch on later, we have plans to expand to the Northeast Falls Creek area, so the other side of the water. I think Bruce talked about this. This is essentially very high level how our system works. So our Falls Creek Energy Centre is actually co-located with a sewage or a wastewater pump station. And so basically the sewage, which is warm, gets diverted into our facility. It's run through screened and run through the heat pump. And then we send out hot water to our customers, to the building level. And at each building, there's an energy transfer station where we basically transfer the heat over to the building side. And this is our I guess, point of connection, or this is where our level of service is delivered at the building level. Within the building, it's up to the building mechanical system and company to distribute that heat to the individual units. So we bring it to the building, and then the building distribute within it. Because a lot of our customers are mixed use, either residential or mixed use. We do have some big standalone non-residential customers like Science World and Emily Carr and the flagship MEC or MEC building on Main and Second. And so then the cooler water comes back through our pipe network. We've an insulated pipe network, and comes back into the pump station. And then on the sewer side, for anyone who's interested, we send back the cooler sewage, and it makes its journey along to the Iona wastewater treatment plant, which is out near the airport. This is a picture of our heat pump, our train heat pump, which has been working away since 2010, 3.2 megawatts. And then in addition to that, we do have 24 megawatts of boiler capacity, gas boiler capacity, which we use for those winter peaks and for resiliency. We are able to keep our environmental performance up by burning renewable natural gas, which is a product that Fortis BC sell here in BC. And what's interesting is the plant, when it was built in 2010, you know, the team that built it knew that as the system grew, we'd need more low carbon energy, and so a space was left within that building, which I'll show you now, to accommodate a second heat pump or another technology to produce low carbon energy. And so that's the big project we have ongoing at the moment, is to install what will be a second sewage heat pump, this time 6.6 megawatt capacity. And so it's a little busy, I guess, but this is a drawing of the Falls Creek Energy Centre. Here you can see this is the existing heat pump. That's the photo I showed you on the last slide. And then mirroring that within this space is the space that was left for the additional capacity. And so even though they're similar in size, I guess technology improvements over the years has meant that a similar sized heat pump is now getting more than double the capacity. So in addition to providing low carbon energy, I wanted to highlight some successes we've had over the years. We have been very successful in securing grant funding. We got a 10 million, so pre-2010, when the system was being developed and the Falls Creek Energy Centre built, we secured over 10 million in loans, grants at the time from UBCM and the feds. And last year we were very happy to be announced for Clean Communities funding, or CCF funding, which was a combination of provincial and federal money. And we also secured a grant and a loan from FCM. This in fact is our mayor and the provincial and federal ministers announcing it. And I didn't point out earlier, this is actually the stacks of our energy centre, because the energy centre is in quite a dense residential or urban area. When the stacks went in, this was actually designed as a public art piece, and so it's designed as a hand, and these are the fingers, and these they can light up. So it becomes a feature of the Vancouver skyline, along with BC Place and Science World. We feel we demonstrate leadership in the low carbon energy, district energy world. We were the first application of sewage heat recovery in North America. We currently chair the C40 cities clean energy network. so get to exchange information with cities all over the world. And we also chair a local district energy working group here in the Metro Vancouver Lower Mainland region. And in fact, some of our municipal neighbours, City of Surrey, City of New West, City of Richmond, are progressing their own sewer heat recovery plans. So the technical expertise that exists within the NEU team has definitely been shared with local partners as they develop their systems. We value community engagement. Pre-COVID, unfortunately not at the moment, or maybe the operators would say fortunately, we're not doing any tours, but we did up to 300 tours a year pre-COVID. We participated in like the City's Doors Open event and got record numbers of people through the energy centre, and we get some media interest here, definitely locally. And I think we demonstrate continued innovation. You know, we're pushing the envelope on sewer heat recovery with the second heat pump. We also successfully recovered heat from one of our buildings, which I'll touch on in the next slide, one of our commercial customers. And I know Bruce has mentioned Shark. In addition to energy recovery, they also have a filtration unit that we've piloted for the last number of years, which screens the sewage before going into the heat pump, and has saved us a lot on water consumption. So moving to the, I guess, current big projects and the future, I've talked about the Falls Creek Energy Centre and our expansion, talked about our Mount Pleasant peaking plant to improve our peaking and our resiliency. This is, so here on Main and Second, there's a large MEC or MEC, it's their flagship store in Vancouver, and they are a customer of ours, and we piloted with them in 2019-2020 a system for them to reject their heat into our system, and so it's been successful and has continued. So they are able to use our system, reject their heat, and cool their building in summer, and so it saves them rooftop space, which they're utilizing as a green roof and for rainwater capture. And it actually, the last two, in 2020 and 21, 1% of our energy came from this building. So small but significant. And then I talked a little bit about, so we are planning an expansion into Northeast Falls Creek, and for this one we're approaching it a bit differently. We're going to we have an RFP, it's just closed but was out on the street, leveraging the private sector. So we went out and asked the private sector, do you have low carbon heat that you can sell to us? And so can't say too much more about that because it's a live procurement, but it's a different model. This time, instead of the city owning the energy generation, we're going to purchase energy from the private sector, and then we will continue to own the distribution network and the customer interface. And we know we need about 20 megawatts over here. This is a very dense development in Northeast Falls Creek that's being planned. So last slide, I think I've touched on most of this. Our big focus right now is on generation, really low carbon generation. We have our own second heat pump that we're installing, and then leveraging the private sector. We hope to get into negotiating this energy purchase agreement early next year. Also very busy working on the roadmap to 100% renewable, which we committed to do under the Climate Emergency Action Plan. And then kind of paired with that, we're also doing some work on our rate structure. So we're hearing from some customers that they may want an enhanced green product. So like some of our customers may be requesting 100% renewable before 2030. And so if that is the case, we would need a special rate for that customer class. And so we're looking at how that might work. Busy with an asset management plan. Our utility's over 10 years old now, nearly 12 years old. So taking stock of assets and developing a structured asset management plan is a high priority. And then we work together with other city groups on overall system resiliency. And, as we have these added energy generation sources across the network, it will make us more resilient and not so dependent on that one facility at Falls Creek, at the falls under the Cambie Bridge. So I think that's it for me. Lots of exciting work ahead and exciting times as we try to meet the challenge from Council and the climate emergency action plan. But happy to hand back over to Juliette and if there's any questions.